The title of this video is How Big is a Light Year? But as you'll see, that question is really only the starting point for our journey. Astronomers use the term light year as a means of measuring the distance to astronomical objects outside our solar system. The speed of light is very fast, and a light year is the distance that light can travel during the course of 1 year. It follows that a light year is a very long way indeed, and it is that great length that makes a light year a very convenient unit with which to measure astronomical distances. But do we amateur astronomers really understand how long a light year is? Many of us can quote the speed of light offhand, and maybe also the distance of a light year in miles or kilometers, but these figures are so large that their true size is hard to grasp. In everyday life, we instinctively know how big large distances are from our own experience in travelling them. For example, consider a journey of 3,290 kilometres across Australia from Perth to Sydney. By passenger jet, the journey time is only 4 hours. But by car, travelling for 8 hours each day, the journey will take 4 to 5 days. Maybe one way to get a better feel for the size of a light year is to take the same basic approach and consider how long it would take to travel that far using various different modes of transport. We might first try using transport systems that we already have. We might then try using transport systems that are beyond our present capabilities, but which are nevertheless a theoretical possibility. We might even try using transport systems that right now are well and truly only possible within the realm of science fiction. And that naturally leads us on to consider how long it would take us to reach various astronomical objects using those forms of transport so as to see how practicable their use would be. The purpose of this video is to explore those matters, and to do so I'll be using a little computer program that I've cooked up. If it interests you, I'll display at the end of the video a website address where you can download a free copy of the program for your own use. Regrettably, it only works with Windows. What you are presently looking at is the introductory splash screen. It's now time to display the program's main screen. Let's just concentrate on the topmost part of the window. At the left here, you can see the length of a light year defined as being about 9.5 trillion kilometers. Over on the right, the speed of light is displayed as both kilometers per second and, more conveniently for our present purpose, kilometers per hour. If you prefer, these amounts can be displayed using miles rather than kilometers. You can see that the speed of light is about 671 million miles per hour, or about 1,079,000,000 kilometers per hour. Okay, now let's move down to the next section below, which considers how long it would take various modes of transport to travel the distance of 1 light year. Assuming that a motor car travels at 100 kilometers per hour, it would take nearly 11 million years to travel the distance of a light year. Not very practicable. A commercial jet plane would cut the time down, but not by very much. The Saturn V Apollo mission rocket, travelling at maximum speed, would cut the time down to about 27,000 years. The greater speed of the Voyager 1 space probe brings the travel time down further, but it still takes about 17,500 years. Even using the fastest man-made object to date, the Parker Solar Probe, the travel time for a light year would still be about 1,500 years. So it's clear that with current technology, we have no real hope of travelling 1 light year's distance unless we're prepared to invest about 63 generations of passengers in the trip. And then it would take another 63 generations for the return journey. Let's up the ante a bit and consider faster modes of transport that are theoretically possible. We'll start with a spaceship that can travel at 1% of the speed of light, which is nearly 11 million kilometers per hour. Clearly, from the point of view of an outside observer, the journey time will be 100 years. But we also need to consider another matter: time dilation. Very briefly, time dilation causes the passing of time to slow down as experienced by a passenger travelling at speed, as compared with the passing of time experienced by someone else at rest. We can calculate the extent of time dilation by using a simple formula. The faster the travel speed, the slower time seems to pass. However, this effect only really becomes noticeable when travelling at a significant fraction of the speed of light. So here we see that for a passenger travelling at 1% of the speed of light, the travel time for a journey of 1 light year would be 99 years, 11 months and 28 days. In other words, 3 days shorter than the time noted by an outside observer. Of course, only 3 days over 100 years doesn't seem to be a big matter. But consider the position if we increase the travel speed to 10% of the speed of light, which is nearly 108 million kilometers per hour. Now the journey time would be only 10 years, but the time experienced by a passenger would be 9 years, 11 months and 12 days, a difference of 18 days. 50% of the speed of light is nearly 540 million kilometers per hour. At that speed, the journey time would be 2 years, but to a passenger it would appear to have taken only 1 year, 8 months and 23 days. By now, time dilation has reduced the passenger's journey time by 3 months and 7 days. It's not possible for baryonic matter, like a spaceship and its passengers, to travel at the speed of light. But if we assume that 99% of that value could be achieved, then our travel speed would be a little over 1 billion kilometers per hour. The journey for a light year would take just 1 year and 3 days, while to a passenger only 1 month, 21 days and 15 hours would have elapsed. Okay, we've explored what may be theoretically possible, but let's go one stage further and dip into the possibilities offered by science fiction. Let's assume that we can take advantage of warp drive. Simply put, warp drive works on the basis of shortening the journey distance rather than increasing the travel speed. It assumes that the fabric of space-time, here represented by the blue film, can be warped or bent back on itself so that any 2 points can be brought closer together than would be the case if their distance was measured the long way around the bend. If then some kind of bridge, usually referred to as a wormhole and shown here as a yellow tunnel, could be found between the 2 points, it might be possible for a spaceship travelling at less than the speed of light to use it as a shortcut. In that case, the journey time between those points would be shorter than if the long route all the way around the bend had been taken. By comparison with the long route, the journey time would be comparatively short. However, for an observer in normal space-time, that short journey time will have been spent covering the full distance between the 2 points as measured the long way around the bend. Thus, to that observer in normal space-time, the spacecraft may appear to have travelled faster than the speed of light. First, let's consider a warp drive equivalent to 10 times 99% of the speed of light. Note that we don't say at 10 times 99% of the speed of light, because that would imply actual faster than light travel speed, which is prohibited. 10 times 99% of the speed of light appears to be 10.6 billion kilometers per hour. In this case, a light year can be travelled in 1 month, 6 days, 11 hours, although it would appear to a passenger to take only 5 days, 5 hours and 9 minutes. Increasing the warp drive speed to an equivalent of 100 times 99% of the speed of light appears to produce nearly 107 billion kilometers per hour. This results in a travel time of 3 days, 16 hours, 43 minutes, and for a passenger, 12 hours, 30 minutes, 59 seconds. For no particularly good reason, let's call speeds above 100 times 99% of the speed of light hyperdrive. A speed equivalent to 1000 times 99% of the speed of light appears to deliver 1 trillion kilometers per hour. And the journey time becomes just under 9 hours and only 1¼ hours for a passenger. Going wild and assuming a speed equivalent to 1 million times 99% of the speed of light results in an apparent speed of 1 quadrillion kilometers per hour. This gives a travel time of just 31 seconds, while a passenger would experience only 4 seconds. Having got a feel for how long it would take to travel the distance of 1 light year using different modes of transport, let's now turn to the practical application of the speeds that we have been considering. To do that, we'll need to view the lower part of the program's window. We'll start by reverting back to current technology using a car. Of course, this would have to be a magic car because it must be able to travel through space. At the car's speed of 100 kilometers per hour, it would take a bit over 5 months to reach the moon. However, the car would take 1,654 years to reach Saturn, so we'd better select a faster mode of transport. A plane would take 207 years, so that's not an option either, even if magically it also could travel through space. The Apollo Saturn V moon rocket could get us to Saturn in 4 years, and to the moon in just 9½ hours. But wait a minute, didn't it take the Apollo astronauts 3 days to move from Earth orbit to lunar orbit? Well, that brings us to how this program is constructed. It takes a very simplistic approach to calculating journey times. It assumes that the selected speed, in this case 40,000 kilometers per hour, will be maintained from start to finish, without regard to the need to ramp up speed from a standing start and to reduce speed before the journey's end. It also assumes that the journey path will be a straight line, whereas in practice, especially for solar system travel, past journeys have taken quite circuitous routes so as to take advantage of gravity assists from other objects along the way. And lastly, the distances to Saturn and Pluto can vary quite substantially depending on where they and the Earth are located in their respective orbits around the Sun. For convenience, the program assumes a fixed distance to each of those planets that is simply the mean of their orbital distances from Earth. It's because of the first of these assumptions that we see a significant difference between the reported travel time to the Moon and the actual journey time. However, the extent of any error will reduce the longer is the journey being considered. If these discrepancies in the travel calculations irritate you, fear not. They mostly fall away when we move to using theoretically possible modes of transport and beyond. Let's consider travelling at 1% of the speed of light to Pluto. The reported travel time of 22 days might actually be out by a few days depending on whether Pluto is closer to us or further away from us than its assumed mean distance. Nevertheless, our reported figure is in the right ballpark. And at that speed, our spaceship would reach the Moon in 2 minutes and Saturn in 5 days. Increasing the speed to 10% of the speed of light drastically reduces travel times. Now Pluto can be reached in 2 days. Time now, I think, to turn to destinations outside the solar system. Starting with the closest object to us, the Alpha Centauri star system, which is 4 light years away, a spaceship travelling at even 10% of the speed of light would still take 40 years to get there. And by the time it got back, 4 generations of passengers would have been involved. Would we be prepared to invest in such a journey, knowing that by the time the spaceship returns, it will be our great-grandchildren who will be meeting it? But such considerations completely fall by the wayside when we consider a journey to the Great Orion Nebula. Even though in galactic terms it's our next-door neighbour in our local arm of the Milky Way galaxy at 1,600 light-years distance, it would take our spaceship 16,000 years to get there. So 10% of the speed of light is clearly not fast enough for most travel within our Milky Way galaxy. Let's try 50% of the speed of light. Even that's not fast enough to get us to the Orion Nebula, taking 3,200 years. So we need to go even faster at, say, 99% of the speed of light. Nope, that's going to take 1,616 years. So, we can conclude that, apart from going to Alpha Centauri and a few other very close-by star systems, we have no real hope of reaching destinations elsewhere in our Milky Way galaxy, unless somehow we can overcome the speed of light travel limit. It's time to turn to science fiction. Travelling to the Orion Nebula by warp drive, equivalent to 10 times 99% of the speed of light, brings the travel time down to 162 years, or 23 years for the passengers. But we hit the same sort of question as before. Would we be prepared to invest in a journey that would take 12 generations for the round trip? It would be our great-great-great-great-great-great-grandchildren who would greet it on its return. Thus, even a speed equivalent to 10 times 99% of the speed of light is not really fast enough for our purpose. A speed equivalent to 100 times 99% of the speed of light would bring the time down to 16 years, and so a return trip of 32 years is arguably feasible, but would it likely draw many volunteers for its crew? Maybe, since they would age by only 4 years. But what about a journey to the Lagoon Nebula? In galactic terms, it's quite close to us, located in the Sagittarius arm of the Milky Way, a neighbouring arm closer in towards the galactic core. At our chosen speed, the journey would take 53 years, or 106 years for the round trip. That's not quite so feasible. In which case, what about 1,000 times 99% of the speed of light? Now we're talking. Only 5 years to get there, and 10 for the round trip. To the centre of the Milky Way, a journey would take 26 years, and that might be accepted as a reasonable ask, even though it would probably be our children meeting it on its return. Well, so far so good. For travel within our quadrant of the galaxy, we only need to aspire to a travel speed equivalent to 1,000 times 99% of the speed of light to meet our needs. But for journeys further afield, to more distant parts of the galaxy, which is 100,000 light-years across, this speed probably won't be enough. And if we aspire to extragalactic travel, then 1,000 times 99% of the speed of light definitely isn't going to cut it. It would take 165 years to get to the Large Magellanic Cloud, which is a nearby satellite galaxy of the Milky Way. So now we need to bring the big guns to bear. Let's suppose that we can travel at 1,000,000 times 99% of the speed of light. Finally, we've reached a state where space travel can be contemplated as a matter of course. Just under 2 months for a trip to the Large Magellanic Cloud, or about 8 days for the passengers. 2.5 years to the Andromeda Galaxy, our nearest neighbour beyond the Milky Way system, and 23 years to the Whirlpool Galaxy, some 23 million light-years distant. Reverting back to closer destinations, at this speed we could reach Alpha Centauri in 2 minutes, the Orion Nebula in 14 hours, the Lagoon Nebula in just under 2 days, and the centre of the Milky Way in 9.5 days. But before we get too pleased with ourselves, we should remember that our favourite space opera heroes seem to be able to pilot their spaceships halfway across their galaxies in no more than a few minutes. It seems that we have still a lot to learn. If you want to use the program yourself, you will find a download link at the following web address: https://davesAstroTools.weebly.com. As a postscript, you can find another page in the program where you can enter your own values for travel speed and destination distance, and then get the resulting travel times both as seen by an outside observer and as experienced by the passengers. It's fun to play what if. Let's assume that our civilization has advanced to the level where we can reach a travel speed of 33% of the speed of light. We plan to make a journey 3/4 the way across the Milky Way, a distance of 75,000 light years. We obviously can't travel through normal space-time, since that would take 3 times 75,000 years, which is 225,000 years. So we need to find a shortcut wormhole. The question is, how short does the wormhole need to be to give us an acceptable travel time? Our scouts have found a wormhole that cuts the distance down by 10,000 times, but is it sufficient? Although the length of the wormhole is only 7.5 light years, the journey would still take nearly 23 years, probably too long. A shorter wormhole is needed, but how much shorter? 1/10 millionth of the normal distance is 71 billion kilometers, and that gets the travel time down to 8 days. But to match our favorite space opera pilots and get the time down to just 12 minutes, we'll have to find a wormhole only 71 million kilometers long. Compare that to the normal space-time distance of 75,000 light years, and you'll see that we're talking about an extreme warping of space-time. Now perhaps you may view space travel sequences in your favourite space operas in a completely new light, and possibly with an increased degree of skepticism. I hope that you enjoyed this little video, and thank you for watching.